Welcome back to a course on sequence and series of functions. In this lecture, we are going to discuss about Dirichlet test. Here, Bn of x is a excuse me. Bn of x is a monotone function of n for each fixed value of x. That means we don't have we are fixing a value of x, and just when we treat this as a function of n, we should have this to be a monotone function. Okay, and this tends uniformly to 0. So that means that when we treat this Bn of x as a sequence of functions, that has to converge uniformly to 0. And if there exists a number k independent of x and n such that for all values of x this thing is happening. Now we have another sequence un of x such that this is uniformly bounded. Okay, that means that we have a monotone function of n which converge uniformly to 0, and we have a uniformly bounded function, bounded sequence ur. Then the series formed by multiplying the corresponding terms is uniformly convergent on AB. This is what this Dirichlet test says us. Okay, since Bn of x here without loss of generality, we can assume that it is monotonically decreasing. If you want to assume monotonically increasing, yes, you can do it and just use the ideologies that we have done in the previous test, that is Abel's test. Okay, now without loss of generality, we can assume this is monotonic decreasing function of n. Then if it is monotonically decreasing and it is converging to 0 as well, right? So we would be able to identify epsilon such that this thing happens. And here it is said that it is a positive monotone decreasing. That is why it is 0 smaller than or equals Bn of x smaller than or equals, usually it is epsilon. For our convenience, we have taken it to be epsilon upon 2k. Now we apply Abel's lemma again to this function ur, that is to the sequence ur. And now when we calculate this quantity, we just see that this is this quantity, and further simplification gives us that it is less than epsilon. Now through Cauchy criterion, we can write this as summation I running from 1 to n plus p minus summation r running from 1 to n. So through Cauchy criterion, we have justified that the series converges uniformly for every value of x in the interval AB. Now with this test, we will have to justify that the given series converges uniformly in every bounded interval, but that shouldn't it is not convergent absolutely for any value of x. So first of all, let me just give you the I am not going to solve this completely, but I'll give you the hints in which it can be solved. First of all, we observe that whether be it any bounded interval AB, we would be able to identify k such that absolute of x is less than k. Suppose if your A, B both are negative values, then obviously absolute of A will serve as your k. If A is negative and B is positive, then look for the absolute of A and absolute of B, whichever is maximum, that will be your k. In simpler terms, your k is going to be maximum of absolute of A comma absolute of B. Okay, and here notice that here our Bn is x square plus n upon n square, and un is minus 1 to the power n. So here our un is oscillating finitely. Okay, here what is the condition that we need to establish? It is uniformly bounded, right? The series is uniformly bounded. So here what would be the series sum to? It will either sum to minus 1 or 0. So it means that 1 will serve as the bound, right? So it oscillates finitely, hence it is a bounded one. Now observe Bn, that is x square plus n upon n square, which converges uniformly and decreases to 0. Okay, this can be compared with k square plus n upon n square, so which is basically what it is comparable it is comparable, and this quantity converges to 0. So if the bigger quantity converges to 0, obviously the smaller quantity has to converge to 0, since it is a sequence of positive terms. Okay, now just apply your Dirichlet test. You would be able to justify that it is uniformly convergent. Now to prove it is not convergent absolutely, just substitute this, just take the absolute value. You are seeing that it is x square plus n upon n square. When you try to examine the convergence of this series, you would compare this with 1 upon n. Okay, since summation 1 upon n diverges, we come to a conclusion that summation x square plus n upon n square diverges. That means it is not converging absolutely. Moving to the next problem. Here we need to prove summation cos n theta upon n to the power p and sin n. Okay, whatever we prove for cos, that will be applicable for sin as well, in the interval alpha comma 2 pi minus alpha, where alpha can be any quantity between 0 and pi. Here when we'll have to prove this is true for p bigger than 0. Whenever your p is greater than 1, you can very well make use of m test, that is absolute of cosine n theta upon n to the power p is less than or equals 1 upon n to the power p. So through m test, for p value greater than 1, we can prove that it is converging uniformly. Now for the case when p lie between 0 and including 1, we will take bn to be 1 upon n to the power p and u1 is cos n theta or sin n theta according to the problem that we are dealing. And what should be the case with bn? It should be monotonically decreasing, positive and converging to 0. That is happening here. And what about this un, summation un? We will have to check, right? So summation un can be expressed in this form, and through some trigonometric identities we are able to see that it is smaller than or equals cosecant alpha upon 2. So which proves what? It is uniformly bounded and bn converges to 0 uniformly. Apply your Dirichlet test, we justify that it converges uniformly. And moving further, we have the next question, that is summation log n plus 1 whole power minus x is converging uniformly in any interval theta 1 comma theta 2, where this theta 1 and theta 2 lie between 0 to 2 pi. Okay, so we are not including 0 as well as 2 pi in this case. So first of all, whenever we have values in this interval, we observe this log n plus 1 to the power minus x is a positive monotone decreasing function of n, and of course this is smaller than or equals log n plus 1 to the power whole power minus theta 1. Since it is monotonically decreasing, the first value, the initial value would be the upper bound. So with this absolute of just a minute. There is a typo in the question. It is multiplied with cos nx as well. So this quantity has to be multiplied with cos nx as well. That is why we check that quantity, and this is 1 upon sin x upon 2, and this would be maximum of this quantity. Now that we have established all the requirements, that is, we have proved all the hypotheses of Dirichlet test, with which we can very well conclude that it converges uniformly. Okay, so why we have not included 0 and 2 pi? It is just that when x is taking the value 0, cos 0 is 1, cos 2 pi is also 1. So we do not want that to happen here. Okay, and obviously this bound is 1 upon less than sin x upon 2. This is what we have. Okay, if it is equal to 0, then we will have 1 upon 0, which is infinite. So it is not uniformly bounded. When it is 2 pi also, it will be sin pi. Even in that case, what will we have? We will have 1 upon 0, that is again unbounded. We do not want unboundedness here. If the 0 or 2 pi is included, then it is not uniformly convergent. Your Dirichlet test is not going to help you. Okay, since we have excluded these 2 points, we were able to do this, and by Dirichlet test we conclude this convergence is that this converges uniformly. That's it. Thank you.